right? So to have the equal pressure, you need to decrease the density, and as soon as you decrease the density in these flux tube, they will come out. Okay, do this exercise. That's interesting. So people have done simulations based on this concept, and what you find is something like this. So the sun is rotating. Again, it's a simulation putting in an artistic way. Okay, so they will open it, and then there is this convection cell where the field lines are being churned around by differential rotation, and this is the number of sunspots being plotted. So you see it's going up and down depending on how the field is behaving. Okay, this is done by people at IUCAA Kolkata, depending on this group. Okay. If you compare what the field lines are looking up into the upper atmosphere, then from photosphere you can just extrapolate the field as lines of forces, and then you would like to see similar thing in the upper layers of the atmosphere, and when you start looking in them, then you see these two kind of structure which are bright. They're essentially mapping the magnetic field lines which are rooted into the surface. Okay. Now since you're
So if the sun was not rotating in the first place, so we won't see any sunspots.
If the sun was not rotating, then you would not see a sunspot. This is what I would think. Because you have magnetic field which is very weak. Right? That's a seed magnetic field. We get the charged particles moving, they provide. But the differential rotation actually enhances it. Churns around, put the magnetic energy, right? And that enhances the flux in some sense, right? And that's what you see all these sunspots and dynamic. The question is, the sun is still rotating, but you have dip, right? It should always increase. Why does it start to decrease?
Exactly. Like why does the field orient suddenly?
Exactly. Sun does something which is not yet explained. Okay. So if you have a better technology and better camera and you can go to space, then you can make observations like this. So this is the sun you are familiar with. You can measure, rather like you can tune the telescopes which are at different temperatures. You can take the photographs of the sun. You can also measure magnetic field on the photosphere. Okay. More X-ray emission. This is X-ray. So essentially the photons which are emitted at 4 to 6 million degrees, those are the photons you are collecting. Here is roughly like 1 million degree, 500,000 and less, and this is the photosphere. Okay. So this is the hot layer of the atmosphere. This is the coolest layer of the atmosphere. This is magnetic field, right? Now the question we posed earlier, that if the surface is 6,000 and the upper layer is 1 million degree or beyond, how do you explain it, right?
So, but is the upper layer really 1 million degree, or I mean the temperature? It may not be a thermal effect, the ionization. Maybe it's
electron temperature.
Else.
Like what?
But I mean, is it?
These are thermal radiation. They are not non-thermal. They are thermal radiation.
Yeah, the radiation is. I'm talking about the thing that caused the excitation of the iron.
Yes.
Is it necessarily due to light coming from thermal radiation? The excitation of the iron.
No, these are because the free electrons. The free electrons are moving with a speed which corresponds to the kinetic energy corresponding to something 1 million degree. So they are knocking off the atoms which are there. The photons which is coming from the photosphere, it takes about 8 minutes to come to you, right? So, and the density is so low in the corona that they don't really encounter with the free electrons, but rather they get scattered. So all the pictures or the features you see in the solar eclipses, they're in white light, right? I'm showing that corona, the upper layers are emitting into 1 million degree, right? But then the question is that how do you see these structures in white light, right? And the reason is that these white light photons are coming all the time to you, and depending on what structures you have on the way where the free electrons are there, they are getting scattered due to these free electrons. As a Thomson scattering essentially, right? So when you see a structure in eclipse which is, remember it was something like that, and then you have structures like this. Right? So there are confined regions where you have more electrons, which are representing more scattering. Okay? Didn't have good sleep last night, did you? Huh? No? Yes? Is it clear?
Okay, but then we still don't know why those electrons have such a high energy.
Yes, we don't. We don't. All we know that they have because they are emitting in X-ray. Right? One electron is just going up and down, so it's producing a photon which is million degree because the energy levels are such. Okay?
Are they somehow confined by the sun's light?
Magnetic field. Think about it. We have to live with it. So we better get ready and prepared. This is the Earth. The radiation is coming, interacting with the Earth's magnetosphere field. These are not observations. These are just cartoonish way or of representing that what might be happening based on various informations from different sources an artist could gather, and so aurora, some pictures that have been taken and put it together. Okay. Now this is one thing. The other thing is that sun is, I'm sure you have seen such diagram by now. Not yet?
Not
Yes,
in,
no?
not in school.
Huh? Not here. Not here yet. Okay. So this is essentially this is called Hertzsprung-Russell diagram, and what it shows here is the luminosity. Now everybody knows by now what luminosity is. It's some sense of measure of brightness of a star. And this is the temperature. So temperature is increasing this way. This is a kind of a peculiar plot because most of the time when you do plotting x and y, x is increasing this way and y is increasing this way. But here the temperature is increasing this way and the luminosity is increasing this way. Okay. So remember that. Most of the stars, they fall in this line here. It's called the main sequence. And that is essentially because the hydrogen burning at the core keeps happening, and then when that happening is starts, the burning of the hydrogen starts in the core, and for the time being it keeps burning there, the star remains to be main sequence. Okay? That's a layman definition. Somebody will talk to you about stellar structure and evolution. Hopefully they will go into more detail. And then in the various stages of evolution, you will have giants, supergiants, and when they die, some of them will become white dwarfs and various other stages of evolution. What am I showing is that sun is nothing but just a star which is just following in the simple main sequence. It's the nearest star, so you see it in its glory details. You might not have seen it, but I will try to show you some things. And so if you want to try to understand all these stars, it's good to try to combine what you have learned from the sun and see if you can try to extrapolate, because any star you look in the sky, they will look like a point source, right? But the sun is not a point source. So whatever we have learned in last 30-40 years based on the technological development, if you can try to incorporate that into your understanding and try to understand other astrophysical objects, that will suffice in terms of studying astrophysics. Now solar physics has a problem. When you talk to physicists, okay, and you say that you're doing solar physics, they will say, oh, he's not doing physics, he's just doing astrophysics. Talk to astrophysicists, oh, he's just looking at a small star, he's not astrophysics, it's not cosmology and large scale structure and all, right? So if you start doing solar physics, be careful, that you really have to prove yourself right that solar physics is both physics as well as astronomy. Okay? Right, and you all know that it has a family of all these planets. Unfortunately, one of them is kicked out of the house. So it's an X-planet now, which is Pluto. And you have asteroids and comets and various other objects. And our life depends on it. And just show you pictures. Okay, no sunlight, no life. Okay, now do you know some statistics, numbers about sun? What the radius is like? No? Does it really make sense? Maybe by the end of the lecture you will be able to join the dots together and all these numbers will start making sense to you. It's 4.5 billion years old, so it's roughly about 10 billion years is the lifetime. So we have a long way to go, generations and generations. if we don't kill ourselves in next 100 years, sun is not going to kill us, right? So that's the masses. Our energy source, the radius is 700,000, mass and temperature, right? This is just to give you an idea that if you just go along the diameter, you can roughly fit 108 Earths. One of these spots, tiny dots here, they could be as big as your whole Earth. Okay, so the diameter, what's the diameter of the Earth?
6,400.
The radius or diameter?
1 lakh radius.
Radius, right? So diameter is 12,000, right? So these spots could be as big as 12,000 to 20,000 kilometers, the diameter. Okay? And the sun, although the solar system is huge, and all these planets are there, Earth and other Jovian planets there. You know what Jovian planets are? The heavy ones, the Jupiter and Saturn. They're bigger and heavier, but the total mass, the 99% of the total mass of the solar system is actually centered at the sun. Okay? So it goes all the way till Galileo back then, when Earth was considered the center of the universe and everything was going around it. Right? Okay, look at the light, and this is just pitching in that why people are trying to show so much of interest into solar energy, because the energy coming from the sun is huge. Any of you have done some calculation based on this? No? Solar constant, you all have heard, right? Yeah? So from solar constant, you can work out how much energy the sun may be producing, right? So the total energy output is 3.8 into 10 to the power 26 joules a second. Okay? Now, I was giving a talk somewhere, and one small kid, he stood up and he said, when you say torch, what torch you mean? Is it a 3-cell battery or 5-cell battery torch, or which one? So take a ballpark number, right? That is your solar constant, right? So in 20-30 minutes, the sun provides the yearly energy needs of humanity. Okay? And the worldwide energy consumption is 10 to the power 20 joules, which the sun produces within a fraction of a second. Okay? And that's why there is a big need for a clean energy and solar energy. Now, how does the sun produce such amount of energy? Right? That's the question. As a physicist, you'll be asking, and an engineer, you'll be going back, wait, if sun is producing so much of energy, how can we use it? As a physicist, you'll go back and try to ask the question that how the sun is managing to produce such amount of energy. Okay? And it's kind of well understood, and that goes to a lot of modeling people have done about the solar interior, because solar interior you can't really see, right? Now there is a saying that things you see more does not really mean that you understand more about it, right? So people who are doing helioseismology, who work in the interior of the sun, when they have to confront people doing solar atmosphere, they come out and say that you see everything in the atmosphere we don't understand. We see nothing inside, but we understand more, right? Because they can explain this, they could explain the neutrino problem, they could explain the convection, the formation of sunspots and various other things, right, from their theory. So essentially that this is again an artistic view what the solar interior would be looking like. There is a core here where essentially the hydrogen burning is taking place, and then usual heat transfer, right? The energy has to be transferred out because the heat source is there. And the way it happens here is due to radiation. At some point, the radiation stops and the mode of transfer becomes convection, right? Can you think about why would that happen? What might happen? Why the convection takes over at some point?
The liquid.
No, there is no vacuum yet.
The liquid.
This is still inside. So up to 75%. So points. If I say one solar radius, up till 0.7 radius, the mode of energy transfer is radiation. Above that, in 25%, is convection.
The density of
The density.
gas inside might change. If it's less, then convection is more easier to transfer.
maybe photochemical.
No. So the basic condition for convection is what?
Difference.
The temperature gradient,
Yeah.
right? The temperature gradient becomes very steep. So once somebody said that it becomes open, so the radiation just goes out from the surface, so it cools down faster. Right? And the heat at the bottom becomes more, so the temperature gradient from inside to outside becomes really large at the outer layers, and therefore the whole liquid just becomes unstable, right? Take a really big pot of water, right? And you heat it, then you start seeing convection, essentially because of that fact. Okay? Right, so every second the sun converts about 1 billion ton of hydrogen into helium. And you can imagine if 1 billion ton hydrogen is being converted, 2 hydrogen is essentially heavier than 1 helium, and your mass defect principle will come in, which will be generated into energy. And can you do some things like if you can start doing fusion by yourself, controlled fusion, then again that's another way of solving the energy problem. And there are projects like ITER. ITER means the way, and that is essentially the way in some sense, right? And India is part of it, like which is the RRCAT, and I think IPRE also. Okay. This is showing again the same thing. This is a simulation. So what you do is you put in your computer some kind of geometry. Here in that case is given a 3D slab, where what you have done, you have put in the temperature gradient in such a way that the cube you have in your box becomes unstable, and what kind of convections you will see. Right, so you see all these bright ones which are bringing out the energy, and then the strain. So if you do a Doppler map in front, what you will see an upflow, a blue shift, and then going a downflow, so red shift. Okay, but this is just intensity. So intensity means that it's reflecting the hot plasma coming up, and cooler one is going down. So it's just a cycle. Okay. When you compare that with observation, so this is observation, of course, can't be 3D, so it's just a snapshot. So if you just look at the top picture here, compare with that, do you see any difference in these two?
So white spots. Those white spots.
These white spots here, right? That is the difference, and that's what makes the whole simulation of convection complicated, and that is because of magnetic field. These bright ones here, they are the proxy for magnetic field, which is generated deep down. Okay. Now, how actually the whole convection and fluid interacts with magnetic field? Started a new subject, magnetoconvection, and people still work quite a lot on that, but it still is a non-linear issue.
So,
Yeah.
exactly what is that image and how is it exactly observed?
This one. So yeah, so this is what you could do. I mean, the sun produces photons in all these wavelengths, right? It goes all the way from X-rays to radio and infrared radio, right? What you could do, you could. Do you like photography? No? Have you heard of H-alpha filters being used to take photos? Yeah. So similarly, you can tune some filters which will be sensitive to some particular wavelength windows. Okay. Now this filter was tuned to something called G-band. G-band is something like 388 angstrom. No, 388 nanometers, so 3880 angstroms. And that reflects the molecules, essentially the CH with the CH band and CN band. Okay? And that is like observing essentially I'll show you a plot later on, the temperature minimum level, where the temperature, when you go out, the temperature decreases. So there is a location, a point when the temperature is minimum, and that broke that region. So
this is
in
not,
that,
not the surface.
this is a surface. Surface is defined as wavelength at which the optical depth becomes 1. Okay, that is the surface. This is a surface because the optical depth is 1 here. You can't probe behind, right? But optical depth is a function of lambda. For a given lambda, you can probe down, you can probe up. Okay? So this is now optical depth 1 for that particular wavelength, right? We're essentially looking at the surface in a very layman term, right? Surface could be 100 kilometers thicker, but the temperature would have some fluctuations here. Okay. Right. So one of the biggest achievements in solar studies happened due to Galileo. Okay. These things were simulated and people tried to understand after Galileo's discovery of sunspots, and then various other things which came into picture. And what Galileo did was he had a telescope, he pointed a telescope, took a paper, drew whatever he saw, and this is an animation made using Galileo's original drawings. Okay, it's no big deal. It's available online. You can go and get it. What you find here is that these sunspots are rotating, and also the sun is not rotating on its axis, and the axis is not exactly at the pole at the north, right? This has an angle which is around here, right? So it's a 7-degree tilted. Okay, so it rotates on that. He also discovered various other things, but let's not get into that. Okay, and he also talked about heliocentric system that you all know about, right? And if you look at the sunspots which Galileo mentioned by his drawings, and look at those sunspots by high resolution telescopes, what you see is this, right? So what you have, let's start from this round corner. You have this dark granular pattern, right? You see bright patches, right? So those are essentially the convection cells which are bringing the energy up of granules. And then you have these huge sunspots, and they have various different structures. So you have these dark ones called umbra, penumbra, and this comes because umbra and penumbra was defined. You know when the umbra and penumbra was defined first time? Eclipses, right? So close it, whole thing becomes umbra, and then you see the structures coming out, they're penumbra. So people knew eclipses for a long time, and therefore they defined this. Whatever is dark is just coming out as a umbra, and the rest is coming out as a penumbra. This is taken from an observatory in La Palma. It's an island, Spanish island in Tenerife. Okay. What you can also do is that number of photons from the sun are so many that you don't really need a very large integration time. Right? If the source is distant, right, you have to integrate it for a long time to try to get enough number of photons so that your signal to noise ratio goes higher, and you can make some sensible study with it. Whereas for sun, we get into another problem. We have to cut the number of photons the sun is emitting, because if we don't do it, the telescopes will burn. Right? So you can tune how many photons you want to get, and therefore you can also do look at the animations. So you can take the pictures frequently and put them together. So essentially that will give you how the sun is evolving, right? So if you do that for a sunspot, this is what you will get. Okay. What you're essentially seeing, so this is units in 1,000 kilometers, okay? So count here how big is the sunspot, right? You see these convection cells, and see these filamentary structures going in and out of the sunspots.
What is the time scale for this?
You can look at here.
What is it in minutes?
In minutes, yeah. So this one is second, this is minute, this is hour. I'm not too fast to count, so maybe you can do it. Okay? How many people are seeing things going in and how many people are seeing things going out? Going in or going out? In. So that was a problem. When you do a Doppler shift, right? This is just relative, right? When you're seeing relative because the convection is going up, it's so strong around here, then you see these things are going down. But if you do a Doppler imaging, then you see there are mass being ejected out, right? And that is what is called Evershed effect. Okay? That was discovered by John Evershed using a telescope in Kodaikanal. Have you heard Kodaikanal? Have you been there? Yeah? Yeah.
But to Kodaikanal, not to the telescope.
I'm sorry?
To Kodaikanal, not to the telescope.
Yeah, Kodaikanal, many people go because of obvious reasons, right? It's a nice place. But imagine that if you get to live there and you start observing sun every day, right? Right? I'm not going to answer in the first slide and let you go, right? I have 1 hour to sorry, I'll come back to it.
So, also physically on the surface of the sun, are sunspots just pits or some cold material, cold gas regions, or a pit in the surface? Because here it seems like it's a sort of pit. Maybe you just, like you said, the surface where optical depth becomes 1. Maybe for that wavelength, the surface corresponds to some depth in that physical.
Yeah, so if you look at wavelengths where the titanium oxide forms, then you would see this bright. Okay, so there is no hole in that sense.
Okay.
Okay, what you have is, I should have answered him and then you would have been answered, but what you will have essentially is there is less plasma in the white light when you're observing it, and therefore it looks darker. Less plasma means it's cooler, right? So you have a high temperature, cool temperature gases sitting side by side and you're observing from distance, right? Then you only see the high temperature plasma, not the cool temperature. Okay. Now after Galileo, what was the second big milestone which changed the whole astrophysics, not only the solar physics? Can somebody guess? Not Jansky. Jansky came very late.
Fraunhofer.
No? Fraunhofer came even later. Before Fraunhofer. Kepler was just doing motion tracking. No, I'm not demeaning him, I'm sorry.
Newton.
Huh? Newton, what did he do?
I mean, the gravity. Split dynamics.
Well, the Newton's gravity thing, of course, changed the
came up with spectra.
Spectra, right? When you start dealing with objects in the sky, right? What are the information you have? Kepler, for example, you track the motions and things like that, so you can understand the dynamics. But if you want to understand the object itself, right? What do you have in mind? In hand.
Light.
You get light, and you get particles, photons and particles, right? Neutrinos, for example, cosmic rays. Right? So neutrinos are difficult to detect. You have to make a big observatories, and if you have heard about neutrino problem, you would probably know. Right? So the photons only comes to your rescue. Right? And photons, they carry their individual identity. Right? So if you understand a photon, you can say a lot about the gas which is emitting that photon. Right? And that's where the term came, the spectroscopy. Right? And spectroscopy actually revolutionized the whole astrophysical understanding in some sense, right? So, you know all this. That's why I said I'll mention radio, because I was going to show this diagram that the sun produces photons. Does sun produce gamma ray?
It might
It's a black body radiation, so it might produce
fusion reaction.
Yes. Why does the black body has to produce gamma ray?
It emits small radiation.
It's a intensity at every point. At least
Is
theoretically.
any object pure black body?
No.
Not
Huh?
except black hole.
It only
hole or black body?
I don't know. I don't want to go there. I'm really scared of black holes. So the sun does produce gamma ray, but essentially in the nuclear reaction site where in the deep, and it just gets converted into white light because of the various collisions it has on the way. Okay. Now the spectroscopy, essentially what you can do with it is you can make these kind of if you use a grating, you can get these kind of diagrams which will be essentially different. So if you have, okay, look at this bottom here or the top, right? This is solar Fraunhofer spectrum, right? What it shows you essentially in the background, you have the continuous emission, and that is what Newton found. He took a prism, get the VI BGOR, right? But if you use high resolution spectrograph, then what you start seeing these dark lines, the Fraunhofer lines. Okay. Now these dark lines, they are happening at a given specific frequency or at a specific wavelength, right? And that is, if you know that wavelength, you understand what element might be emitting or absorbing. So if there is an emission line here, so what you have here, the background is a continuum, and on top you have these bright lines which are the photon is being emitted. In these ones, the photon is being absorbed, right? Now atoms, they don't absorb and emit photons in a random way, right? They have very specified frequency or the energy levels where they can absorb or emit, right? So if you understand such diagrams, right, then you can say quite a lot about the constituents you're looking at. Okay, so essentially, if you get a spectra, they are like bar chart or like barcode for an item you buy in a supermarket, right? Essentially, they read these lines and tell you what the price is, and you get in your bill is whatever thing you like, right? The problem is that these ones are defined by the company, and they will tell you pre-hand. So you design the machine and read it. These are defined by nature, and you have no idea about. So you have to develop models and theories to try to understand it. Okay. I find this is more interesting to do, right? So anybody would try to do physics or astrophysics. Will try to. Doing this, one of the biggest problem of solar astronomy was discovered. Now, discovering a problem and discovering a solution, right? So we are happy discovering a problem. Discovering a solution means you are out of job, right? So discover problems. Once you know the problem, what problem to look at, and you make other people interested into the problem you are looking at, you are in job. Yeah? So keep that in mind. Astrophysics or physics, finding a right problem is very important. So what was done is that during an eclipse, people were only seeing eclipse in white light. So you see all these structures. So again, you see the sun is tilted. You have these, we call it plumes, and then you have these close field lines which are also extending all the way up to 5-6 solar radius. Okay. If you put a slit, right? You all know spectrograph, right? So when I say slit, you know what I mean. Yeah, slit and grating, so it will disperse the spectrum. This is just again a cartoonish way of showing what you find. But what they discovered was that 3 different lines came. This is red, yellow, and green. Okay, at 3 different wavelengths. Okay, and that was a surprise that how when you see everything in visible light, you see these in emission lines, and they didn't know what these could be corresponding to. Okay, and in an eclipse beforehand, they had another line observed, and they found a place for that in the periodic table, and they called it helium because they discovered it from the sun. Okay. After a few years, I think after 100 years or so, yeah, they discovered these, and then they thought that similar way there could be another line are another element in the periodic table which Mendeleev somehow has missed. Of course, he missed many things, but the table he gave was complete, right? And they name it coronium because it was coming from corona. Corona means crown. So when you block the sun's face, you see this crown-like features appearing. So they call it corona. And they said that these lines are coming out of the corona because they were observing outside the sun. Called it coronium. But they never, then they did more studies and they never found a place in the periodic table which would suit or satisfy the conditions they were looking at. Okay? Later on it was found that these lines, so the green line and the red line, the two of them were essentially due to stripping out 13 and 14 electrons from iron, and this one from calcium atom. Okay, calcium 15, I think. So taking out 14 electrons from calcium. Right? Now, how difficult is it, you think, to take 13 electrons out from iron? You don't have any feel about it, right? How difficult it is to take one electron out from hydrogen? How much energy you need? Electron volts, right? So that is the force annihilation potential. Right? So you can keep working backwards and try to work out how much energy you will need to take 13 electrons, and the energy which you need it will be equivalent to a 1,000,000 degree plasma. Okay? I said earlier that the temperature of the sun was 6,000 degrees. Right? Now I'm saying that when you go into the atmosphere, the temperature is about 1,000,000. Right?
But how do we know what the spectrum looks like for a 13-time ionized ion? That's not experimentally possible to recreate.
You can model it.
But
The atomic theory.
So many electrons.
Yeah. So people have done modeling, and the number of lines they produce now is computationally very intensive. But you can do this. And atomic physics is very well understood subject because thanks to quantum mechanics. As soon as it came, people started looking at these. Okay? And that's what, when I said it's discovery of the biggest mystery, right? About solar physics. And about 50-60% of solar physicists are having their bread and butter because of this discovery. Okay? Doesn't it sound interesting? I'm just bluffing. Oh, people bluff quite a lot, huh? So I can bluff. But don't you think it's an interesting problem? Yeah? You can say no. A lot of people find everything non-interesting. Right? Writing a nice code is also very interesting. Okay. Right. So now with the instrumentation and the kind of understanding we have, what we could do, we could measure the temperature as and when you go. So you can model the temperature up till here because the temperature will be going down, and you can measure what is the temperature at the surface because you can look at the spectrum. You can see what black body fits in, and then you can start looking how the temperature might be changing. So what you do, you take observations in different wavelengths, and since you're looking at temperatures which are 1,000,000 degree, you can only get photons into ultraviolet and X-rays, right? And you have to go to space and measure various things. Okay. So if you look here, that's the temperature minimum region I was talking about. Somebody asked me a question about that particular image I was showing. That was taken around this wavelength here. Okay.
So basically by calculating the temperature at the different heights, by using the same method but taking the pictures at different wavelengths, so
yes.
that we are redefining surface for a given wavelength.
Yes. So for example, I'll show you images for that wavelength the surface will be different. But that's why you needed to have one single definition for surface. And if somebody tells you in a technical way what the solar surface is, then it is optical depth one at lambda equals to 550 nanometers. Right? That's the definition. So that is one solar radius.
So this won't have been possible without the camera or the lens technology that we have lately.
Yes.